Good day everyone, welcome to our class in Math 111. So today we are going to discuss limit of a function. Since this is a little bit long topic, so let us also divide this into several parts so that you will not be having any difficulty in downloading any of the parts of the lecture if we divide it into a smaller part, fragments of smaller parts. Okay, so before we go to the main discussion, let us see first the objectives of this topic or this lesson. At the end of the period, you should be able to define and interpret the concept of limit intuitively, evaluate the limits of functions and one-sided limits, evaluate the limits of continuous and discontinuous functions, evaluate infinite limits and limits at infinity, apply the concept of limits and continuity to solve real-world problems. Alright? So what is really the concept of limit? So we need to understand the concept of limit because this is the cornerstone of both differential and integral calculus. So we need to understand what does this limit really means. Otherwise, we'll be having difficulty later on. So what do you mean by limit? Well, we have this concept that a limit means getting as close to something as you can without actually getting there. Okay, is that clear? A limit means getting as close to something as you can without actually getting there. And here we have what we call Zenos Paradox. So it says that a man standing in a room cannot walk to the wall. It means that he can only get as close as he can to the wall but not to the exact position of the wall. Okay, is it clear? So if there's a wall and if you want to walk towards the wall, so you have a limit. Your limiting position is just very close to the wall, but you cannot be in the position or the exact position of the wall. So that is Zenos Paradox. In another scenario, we can never be Jesus Christ. As mentioned in this paradox, we can never be Jesus Christ. We can only be as close as Him by imitating His actions and by obeying or doing His commandments, especially His commandments of love. Love one another as I have loved you. Okay? So mathematically, a limit means this is the intended height of a function. So when we speak of a limit in mathematics, so this is what we call the intended height of a function. Now let us consider the function defined by this expression. F of x equal to x squared minus 2x minus 3 divided by x minus 3. Now let us investigate the function values as x gets closer and closer to 3. So what will happen? In our previous discussion about functions, we know that if x equal to 3, what will happen to this expression, or what will be the function? If x equal to 3, so what will happen? If this x equals to 3, then 3 minus 3 this becomes 0. In our discussion on function, we have to avoid this scenario because this will make the function undefined. We have to avoid the denominator equal to 0. Okay? But anyway, we are not concerned for discussion today. We are not concerned with the value of the function when x equal to 3. So what we are after of is to look at the values of the function as x gets closer and closer to 3. Okay? So this is what I've said a while ago. The function f is not defined at x equal to 3. And we say that, or we can say that the domain of the function f is expressed in this expression r minus 3, meaning the domain of the function of this function are all real numbers except number 3, because number 3 here will make the function undefined. So this is the exception of the domain. Okay. Now let us consider the same function defined by this expression, and now let's assign values of x, like x equal to 1, x equal to 2, x equal to 2.5, x equal to 2.9, x 2.999, and x equal to 2.9999, tatlong 9 to class, and solve the corresponding values for f of x and write the result in the table. And also we have to assign values like this: 5, x equal to 5, x equal to 4, x equal to 3.5, x equal to 3.1, x equal to 3.01, and x equal to 3.001 to x, and then solve for the corresponding values for f of x, and then write the result in table 2, now as shown in this table. Okay, so we are given this table, so we need to fill this up. Okay, so fill this up. What's the value of f of x when you have this corresponding value for x? Okay, and so do with the second table. Okay, so this is our table 1, so we call it T1, and this is our table 2, or we call it T2. Okay, so substituting, we have this result. Okay, and now let us observe, let us examine what happens to f of x as x approaches to 3. So we have x, ang value ng x plus is increasing from 1 up to 2.999. So it means ang limit natin dito is 3, because the limit here is 3, because this, when this becomes 3, this becomes 0, so the function becomes undefined. So we've noticed that our f of x as x approaches to the value of 3, when x approaches to 3, meaning when x gets closer and closer to 3, so we have our f of x gets closer and closer to, it gets closer to the value which is equal to 4. Alright? So as x gets closer and closer to 3, our f of x gets closer and closer to 4. Alright, so this is for table 1. Okay? And for table 2, we've noticed that as x approaches to 3, but this time class, ang value ng x natin is decreasing. So as x gets closer and closer to 3 also, okay, so in either scenario, our x is getting closer and closer to 3, so what happens to our f of x? So you've noticed that f of x also going down from 6 going to 5, 4.5, 4.1, 4.01, 4.001. So where do you think this values goes to? So it will also goes to the value of 4. So we can say that as x getting closer and closer to 3, decreasing from 5 to 3, approaching 3, so we notice that f of x is also get closer and closer to 4. Okay, so we say here that x equal to 3 is the limit, no? We say that the value of x is approaching 3 or gets closer and closer to 3. So this should be our limit. Our f of x also, this would be the limit of our f of x. Alright, so you can, another way of saying this situation or scenario is by graphing the function. So to graph the function, or to to graph the function, you need to plot the points. So you have the pair of abscissa and ordinates here. You just plot this. Alright, so we just use these Cartesian coordinates where this is our x-axis, this is our y-axis, and we know that y is a function of x, or the value of the value of y nagdepende sa value ng x. So we have y as a function of x. Okay? So another way of saying it is by plotting the points and then graph the function. Okay, so for example, if when x equal to 1, f of x is equal to 2. X equal to 1, f of x is 2. So we have the point here. The point is somewhere here. Okay, when x equal to 2, f of x equal to 3. So the point is somewhere here. When x equal to 2.5, so 2.5, our f of x is 3.5. So 3.5 is somewhere here. So more or less the point is also here. When x equal to 2.9, so x is 2.9, so assuming the point is here, we have 3.9. So assuming this is 3.9 here, okay, so we have this point. Okay, if and so on and so forth, when x is very close to 3.999, so we have the value of f of x is very close to 4 or 3.9999 also. Okay, so it's somewhere here. This is just approximate. And then when x equal to 5, so the next table, so when x equal to 5, we have f of x equal to 6. So this is our f of x equal to 6 when x equal to 5. So just draw a line, vertical line, and draw a line, horizontal line. The intersection would be the point. Okay, so we have the point here. And when x equal to 4, so we have f of x equal to 5. Okay, so f of x equal to 5. So draw a horizontal line, draw a vertical line. The intersection point will be the point. Okay, and so on and so forth. So I say, for example, when x equal to 3.5, somewhere here, so we have f of x equal to 4.5. So somewhere here. Okay, all right. So we have here a scenario that our x is approaching to the value of 3 from the left, right? From the left. So we started with 1. Okay, so we started from 1 going to 3. So assuming this is our 3 here. Okay, so x is approaching to 3. So our x is approaching the value 3 from the left, and we put it sign here negative. And another x is approaching from the right going to 3. Okay, so we have another x here. So our x, we have a plus sign here, meaning it's coming from the right, and we have a negative here. It means that our value is coming from the left. Okay, so what you have noticed is that as x approaches 3 from the left, so it means our values is increasing from 1 up to 2.9999. We see that the points are also increasing, meaning the value of f of x is also increasing. To where? To what value? So it's going to 4, right? So this is at x equal to 3, okay? But this is not, because it will make the function undefined, so it will be open here. Okay, and then if x approaching to the value of 3 from the right, meaning from 5, you've noticed that the valued function here is decreasing, but it goes to the what value? That's the same value that is also 4. Alright, okay, so we have noticed here from the table 1, as x gets closer and closer to 3, the values less than 3. Now, for the values less than 3, we say that, or we have seen that f of x gets closer and closer to 4. So that's from table 1. Then from table 2, as x gets closer and closer to 3, for the values greater than 3, f of x gets closer and closer to 4. Right? So you have seen here. So our values of x, as x approaches to 3, so we've noticed that our f of x also gets closer and closer to 4. And similarly, this is for the values of x from left going to the right. Okay, so from right going to the left going to 3. So we've noticed that as x gets closer and closer to 3, we've also noticed that our f of x is getting closer and closer to 4. Okay, so we can say that x is the limit. This is also the limit. Okay, so x equal to 3 is the limit, and this is also the limit for f of x. So mathematically, when we speak of limit, so from this scenario class, we can say that as, okay, I delete this one first so that you can read it. Okay, so as you can see here, the number 4, which f of x gets close to when x gets closer to 3 but not equal to 3, is said to be the limit of f of x as x approaches to 3. Alright, so remember that the number f of x gets closer and closer to as x gets closer and closer to 3, so that would be the limit of f of x. So in this case, in this example, the limit is equal to 4. Okay, so I hope that's clear. So in symbol, we write this mathematically as, so mathematically, we write this in symbols as limit of f of x. So in symbols, we write this as limit of f of x as x approaches to 3 is equal to 4. Alright? Any question? Okay. Okay, so I hope you understand this class. So our next topic is about limit definition. We have to emphasize this discussion through this definition class. So if f of x gets closer and closer to a number L as x gets closer and closer to a number C from both sides, then L is the limit of f of x as x approaches to C. So the behavior is expressed by writing. So this is our representation of that definition, that the limit of f of x as x approaches to c is equal to L. Okay? So note the following. In finding the limit of a function as x approaches to a number c, we are not concerned with the value of the function when x equal to c. Alright, so we're not concerned the value of a function when x equal to c. As we have seen, the limit can exist even if f sub c is not defined. Alright, to discuss this further, to elaborate this further, so we have here a mathematical symbol of the concept that you have seen a while ago. Now, the limit of f of x as x approaches to c is L. This is how we read, class, this symbol. The limit of f of x as x approaches c is L. Okay, so that is the definition of our limit based on our presentation a while ago. So as x gets close to a number c, so this is what it means by this expression. As x gets close to a number c, y, which is f of x, gets close to a number L. Okay, so this is the limit, like in our previous discussion, that as x approaches to 3, our f of x approaches to the value 4. So 4 is the limit. Alright? Now, geometrically, so the limit statement, limit of f of x as x approaches to c equal to L, means that the height of the graph y equal to f of x approaches L as x approaches to c. So it means this is the height, class, the height of the graph. So if you cannot remember this, or if you don't understand this, just think of it as the height of the graph of y equal to f of x. Alright? The height that the function y equal to f of x approaches. So the value that it approaches, meaning it goes closer or gets closer and closer to as x approaches to a value which is c, a number which is c. Okay, so like in this illustration here, as you can see here, we have here c. This is our c. Okay, then this is our x, the horizontal value, as x approaches to c. So our x approaches to c. Okay, this is from the left, and we also have here x approaches to c, that is coming from the left, from the right. Okay, and we have here our function. This is the graph of our function. Okay, so this is the graph of our function. Okay, so as you can see here, when x equal to this value here, okay, so ang value ng x natin is nandito. So we have the graph here, and this is the corresponding height. Okay, so this is our f of x. And when x equal to, say, somewhere here, if our x is somewhere here, then look at the intersection on the graph. So this is our f of x. Okay, then as x approaches to c, meaning if the value of x is somewhere here, okay, if it's somewhere here, right, so this is the corresponding value of f of x, and we call it as L. Okay, so as x approaches to c, our f of x approaches to L. Alright? Or if coming from the right, so as if this is our value for x, so there is a corresponding, you just extend this line vertically and the point where it intersects the function or the graph, okay, and then draw the line going to the left, which is perpendicular to the y-axis. Okay, so this is the corresponding value for f of x. Okay, so if x is equal to this value, okay, so you draw a vertical line, intersect the graph, and then draw a horizontal line perpendicular to the y-axis. So this is your f of x, value for our f of x at this point here. Now as x going or moving closer to c, so say at this point, so you see that if you draw a line vertically, it will intersect at this point. Okay, then draw a line horizontally perpendicular to the y-axis. So this is your new value for f of x. And as x approaches from the right going to c, okay, so if it approach here, so it also approach this value L. Alright, so from the left going to C and from the right going to C, so they approach the same value, which is L. So this is what we call the limit. Alright, so the limit of the function. So the limit describes the behavior of the function near a particular point, not necessarily at the point itself. So that is what is meant by the limit or limits. No? It describes the behavior of the function near a particular point, not necessarily at the point itself. So the limit exists for the following. For example, we have this function, we have here c, as x approaches to c, we have here, so shaded portion meaning the value of f of x is defined at this point. Then we have here limit of the function c as x approaches to c, and there's a halo here. Halo, it means that the limit does not exist at this point. Maybe at this value, the value of f of x is here. Okay, but still we know that the limit exists at this point. And similarly to this one. Okay, so the limit L as x approaches to c, we have the limit L. As x approaches to c, we have the limit is L. Same here for A. Okay, so the limit does not exist for the following. So look at this. So from the previous pictures, those are the situation where the limit exists, but in this new or this other picture here, this shows that the limit does not exist. Now for example here, so as x approaches to a certain value, which is in this case we have a value which is equal to 2. Okay, so for the value say from 1.1 from 1 or from 0, so when x equal to 0, 3, when x equal to 1, 3, still the same 3, when x equal to 1.1, 1.5, that is 3, and when x equal to 2, okay, so we have this point. But from the right to the left, when x equal to say 4, f of x is 5, the limit is 5. When x equal to 3.5, the limit is 5. When x equal to 2.1 to 2.5, the limit is 5, and so on and so forth. Okay, so you see here that the limit does not exist. So in this particular situation, uh, the limit does not exist. Okay, so there's no limit in this particular situation. And so do with this graph here. So we cannot find the limit. No matter how much value you are going to substitute for your x here, you cannot determine or you cannot get the value for your f of x as x approaches to 2. No? So as x gets closer and closer to 2, so you will see this curve going uh, closer and closer to this value. Okay, so this is what we call the asymptote. So this is the line which is x equal to 2, where the graph of the function will just get closer and closer, but it will not, or it will never touch. It just getting closer and closer to. So this is the, so there's no limit here. We cannot see, or the limit does not exist in this particular situation or scenario. All right. So for example, if you're asked to evaluate, you're given this function, say x plus 3, you're asked to find the limit of x plus 3 as x approaches to 2. Okay, so now we have to study the behavior of the linear function. Okay, because that is linear. So what is the behavior of the linear function? So f of x equal to x plus 3. So as x takes on values closer and closer to 2 from both sides, so values less than 2 and values greater than 2. So what happens? So this is our illustration class. So we have x plus 3. So our function is x plus 3, f of x equal to x plus 3 as x approaches to 2. So what will happen? So we have here an illustration. Our value of x that is being approached to is, or getting closer to, is x equal to 2. Alright, now let's substitute. We just plug in the values from here. Okay, so we'll start values from the left. We can start with minus 2, or you can even start with minus 3 or minus 4, and then our values is getting closer and closer to 2. Okay, so from the left, our value is approaching or getting closer and closer to 2. Then from the right, we have our, this is our x. X is getting closer to 2 from the left. The other one, our x is getting closer to 2 also, but the variable is from the right. Okay, so this is our value 2 here. Okay, so substituting the values to this expression. Alright, so we see that as the value is increasing from the left to the right, we've noticed that the value for f of x is also increasing, and it gets closer and closer to what? To this value 5. Okay, so as x approaches to 2, our f of x approaches to 5. So this is the limit. As you can see also, as x decreasing from 3 going to 2, from 3 we have 2.01, 2.001. We have noticed also that the value for f of x is getting closer to 5. Okay, so this is what we call the limit. Okay, so 5 is the limit. As x approaches to 2 from left and from the right, f of x, the limit of f of x is equal to 5. And by notation, so we use the this notation here. I'll just delete this one to make it clear. Okay, so the negative number indicated in the arrow, above the arrow, so that indicates that the values are from the left of the number that is being approached to. If you can see that there's a positive here above the number, it means that the values are all coming from the right, going to that number that is being approached. Okay, so I hope this is a very clear, class, because this is really the concept that we need to instill in our mind and put it in our heart, so that later on you will not find it difficult to solve problems that involves limits. Okay, so one is expressed this one is expressed as limit of x plus 3 as x approaches to 2 equal to 5. Okay, so this is the mathematical expression of this behavior, of this situation. Okay, so I hope you understand this. Now, for example, find the limit of x plus 3 as x approaches to 2. So we know that in our previous illustration, this is equal to 5. So this is clearly explained from this illustration, class. So it means that as x approaches to 2, okay, so these are 2 here. These are x. We see that from the left of values, meaning if you substitute values coming from the left, all these values from the left going towards 2, so you see that the values of f of x is approaching to value 5. And similarly, if the values of x is from the right, going to that value which is 2, as x approaches to 2 from the right, so we've noticed that the f of x is also approaching to the value 5. Okay, so from both sides, left, values for x from left side and values of x from the right side, they approach to the same value which is 2, and the f of x for both values or set of values of x reaches or gets closer to the value equal to 5. Okay, so that is what is meant by this expression. So we can say that, so for that particular example, class, this explains clearly what has been discussed in the previous slides. Okay, now another example, evaluate. Now from that illustration a while ago, you have seen graphically how to find the limit. But there are times, class, that you're asked to find the limit mathematically. But this is by graphical solution, you will see the limit of this function, x plus 3, as x approaches to 2. So by graphical method, you see that the limit is found, which is equal to 5. So this 5 here. Okay, so the 5 that you have, okay, so this 5 here that you have seen in this expression is the one that is being approached. This is the height of the function, which is equal to 5. Okay, so for example, evaluate this given expression, limit x squared plus, or the limit of quantity x squared plus x minus 2 divided by x minus 1 as x approaches to 1. So we know that as x approaches to 1, or if x equal to 1, this makes the function undefined, because dividing by 0 makes the function undefined. Okay, so graphically we can show this illustration here. or from this illustration here. Okay, so as x approaches to 1, so we know, you see here a halo, so it means that this is the value where we cannot get the, or it is the point x equal to 1, it is the point for x equal to 1 where we cannot get the value for the function. This makes the function undefined. But actually the limit exists now, as shown in the previous slides a while ago. So the limit exists. So we can see here that as x approaches to 1 from this illustration, so you see that the limit is equal to 3. Okay, so the answer here is equal to 3. So that is by graphical solution class, you have seen that the limit is equal to 3. Later on, you will learn how to find the limit by mathematical manipulations of this. You will see why it's 3, why is the graph is straight line. In fact, you are given here at the numerator, this is a second degree expression, but why is it that the graph is a straight line? So you will learn that later on. So now for now, you just see that by graphical method, you see that the limit of the function as x approaches to 1 is equal to 3. Okay. So again, this is a halo. It means we're not concerned of the exact value here. We're just looking at the behavior of the function as x approaches to 1. Okay, so you can substitute values from the left. Okay, so you can substitute values from the left. All the values here like 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and so on until it reaches 0.9999. So at 0.999, so you have here the values here. Or from the right, going to that value 1. So you have, say, 2, 2.1.9, 1.5, 1.1, 1.2, and so on and so forth. Then again, this is the limit. They will reach the same limit equal to 3 as the value of x approaches from left to this value equal to 1, x equal to 1, and from the right to this value x equal to 1. Okay, so the limit is equal to 3. So you have seen here that the answer is 3. 3 is the limit. Alright, that is by graphical method. By mathematical method, later on you will learn why it's equal to 3. Where in fact, when x equal to 1, this becomes 0. So this makes the function or this expression undefined. Okay, so I hope it's clear. Now another example here, we have a graph of the function given in this, and you're asked, or from this graph you can see that the limit of a function is equal to 2, right? Limit, right? So not necessarily the exact value as of x equal to 2. So this is our x equal to 2 here, x equal to 1, x equal to 3. Okay, so the limit of a function, as you can see from this graph, is equal to 2. So you know that this is 1, this is 2. Okay, now we have here f sub 2, meaning the exact value of the function, so we can see here that as f of x, when x equal to 2, the exact value of the function is equal to 1. Okay, so that's why we have here f sub 2 is equal to 1. That is the exact value of the function when x equal to 2. When x equal to 2, so f of x equal to 1. So this refers to this point here. Okay, now the limit of a function is equal to 2 as x equal to 3. Why? You see, as when x equal to 3, you've noticed that this is a straight line, meaning it's constant. If x equal to 2.5, so that's the same. The limit is equal to 2. This is a straight line. It's constant. So it means that as the value approaches to 3, from for example from the right, if you goes from right to the value of 3, okay, so as x approaches to 3 from the right, so this is constant. Or if uh, from the left, so this is also 2, because you see the graph here, we're referring to this graph. We're talking about this graph. So when the value of x coming from the left towards this 3, limit is, meaning x gets closer to 3, the limit of our function is 2, no? Because this is a constant. So either from the left going to that value 3, or from the right going to that value 3, this is a straight line which is equal to 2. So the limit of the function as x approaches to 3 is equal to 2. Okay, so I hope it's clear, class. This is a little bit confusing, but if you really are following in our previous slides, then you for sure you will be able to understand this. Okay, now f sub 3, exact value of 3. So what is the exact value of the function when x equal to 3? So that is also equal to 2, right? So when x equal to, from here, when x equal to 3, so from this function when x equal to 3, then you have the value f sub 3 equal to 2, because this is constant. Alright? Okay, so it means, class, that the limit of a function refers to the value that the function approaches, not the actual value if any. Again, the limit of a function refers to the value that the function approaches, not the actual value, assuming there's any. Okay, so I think that's all for this part. I will continue in the next part later. And thank you very much for listening. Have a good day to everyone, and see you again in the next video. Stay safe and healthy always. God bless everyone. Bye for now.